And we are now recording. Let me just go through a couple pretty minor announcements. I did have to do a midterm progress report last week, and basically since I knew y'all were all working hard, and I gave you the last test the first test sort of late, I said, and you all been attending, I said, they're okay. So there was nothing to do with that. But the other thing is, not that many people come by early in the morning, but I'm usually here before 8 o'clock. 8 o'clock I'm supposed to be here. Usually I'm here a little before. And usually I'm in the office. I don't start class until 8:30. Okay, that's 4 days a week. I've got 8 o'clock classes, 8:30 classes across the board. But because I had a doctor's appointment last Tuesday, that class lost the last 45 minutes of its class. So what we did, we started that Tuesday 15 minutes early, so that got us 15 of those 45 back. Thursday we did 15 minutes early, so we got 30 of the 45 back. Tomorrow I'll also start 15 minutes early, meaning 8:15 rather than 8:30. So if you come by my office early in the morning, like 8 o'clock, you'll still catch me. But shortly after that, I'll be heading to the classroom to set up, so we'll start class at 8:15. So if you are looking for me early in the morning, and if you don't catch me in the office, then I'm in 205. It's on the door here. 205 is my Tuesday, Thursday, 8:30 class. So I'll be down there. Okay. And that's the only other sort of major announcement. Not major, but minor thing. And I did tell you already, my office hours on Tuesday, Thursdays have changed. First mini-term, they were 11:15 when I finished this class. Wait, no. That's Tuesday, Thursday. 11:15 when I finished my trig class. Used to be until 1:15 when I started physical science. But the second mini-term physical science class doesn't start till 3:15. So now I have office hours from 11:15 to 3:15 on Tuesday, Thursday. Doubles my office hours on those days. But the downside of that is I'm here until 7:45 at night. So, but I got more office hours anyway. Okay. Any questions on anything before we get started? All right. Let's start the slideshow from the current slide. And here we go. This is where we left off last time. Integration as an accumulation process. Now, I've taught this from this text one time before, and I think I remarked then, I don't ever remember a textbook talking about this quite the same way this guy does. And I'm not sure it's all that helpful, or, yeah, it is in some sense, but, okay, let's just do it. The integration formula for the area between two curves was developed by using the rectangle as a representative element. Each new application of integration in the remaining sections of this chapter, an appropriate representative element will be constructed using pre-calculus formulas you already know. Okay. Each integration formula will then be obtained by summing or accumulating those representative elements. Okay. So we'll take the known pre-calculus formula, represent an element with that, and then come up with a new integration formula. Okay? Seems like we've been doing that already, and if it does, we have. So here's one. For example, the area formula in this section was developed as follows. The area was height times the width. Okay? Now, the height that we had was the difference between the f of x and g of x, and the width was the dx, or delta x. So the dA was the height times the width. So what did that become? The area, when you integrate the delta here and integrate the delta there, this becomes A, and this becomes the integral of this dx. And it's just merely f of x dx. And it's going from A to B, wherever you started, F from F and G from wherever you ended. Okay? Okay. Seems like what we've been doing I didn't know we needed to talk about it as an accumulation process. But maybe you do. Maybe it needs this extra reminder of that's what we're doing. And here's the Marcus. All right, no problem. We're on the top of page 449 and near the end of 7.1. Okay? So here's example 6, which is on that page, still in closer to the middle of the page now. Find the area of the region bounded by the graph of y is equal to 4 minus x squared and the x-axis. Okay? And then it said, describe the integration as an accumulation process. It seems like to me, once you found what the area is, who cares what the accumulation process was? You got the answer, but that may be just me. All right. Now, one like this, you can either do it graphically and see what the deal is, or you can use just the algebra part of it and figure out what the deal is. Okay? Do y'all prefer drawing graphs or figuring? Figuring. I like that idea. Okay, here's the first thing I'm going to figure. What in the world does that graph look like? You don't have to tell me, you don't have to plot it, but what does that look like? Y is equal to 4 minus x squared. What kind of a shape is that? Parabola, exactly. Okay? And can you tell me something about that parabola?
I would say currently is upside down.
What?
I would say currently is upside down.
Okay, meaning it's opening downward. Is that what you mean? Absolutely. Why? Because your quadratic term, x squared, is negative. That means it's opening downward. Fantastic. So, the bounded by the graph of that parabola and the x-axis. Well, the x-axis is where y is equal to 0, right? So there you have, it's the difference between those two. Now, the question would be, since it's opening downward, is that even above the x-axis?
Yes.
How? How do you know that?
So it's raised by 4.
Okay, yes, because it's actually a translation of 4 up, or in other words, put a 0 in for x, and you get y is equal to 4. So you know it's starting at 4 when x is 0, y is 4. So I aren't drawing the graph, but we're picturing the graph, and then it opens downward from there. So sure enough, that has to have an area bounded. So then the next question is, what are the bounds? Okay? What are the limits on that? Okay? Now, that would be where that graph intersects the x-axis. And what is always true about the x-axis?
It's flat.
Say again?
It's flat.
It's flat. At what value of y?
0.
Yes, y is equal to 0. So what we can do to find the points of intersection, that's usually what we need to know, right? That would be set this equal to 0, equal to the x-axis. 4 minus x squared is equal to 0. And solve that. How would you go about doing that?
Wouldn't it be 2 negative 2?
Okay, x equal minus 2, x equal 2. Those are the 2 points of intersection of that. So here we're going from x equal minus 2 to x equal 2. All right, it looks like we can start then. Now, one advantage, now I'm backing up on my claim that not really caring to draw graphs. One advantage of drawing this graph, and you probably would be able to think through it, but I'm not sure. Let's just sketch out what we know. You've already told me most of it. Okay? 1, 2, negative 1, negative 2. 1, 2, 3, 4. Right? You said it started here, intersected there and there. So guess what? That's about what it looks like, right? Give or take a wiggle or a jiggle there, here and there, right? Now, especially looking at that, what kind of function is that? As far as even and odd. even function, which tells you this. If we figure the area under here, we can double it because the same area has to be over there, right? So let's make the problem as easy as possible. Let's not go from -2 to 2. Let's go from 0 to 2 and double it. So we have the area is equal to 2 times the area from, that's supposed to be an equal sign, from, second, 0 to 2, perfect. And then what's your function? 4 minus x squared. That's how high you're. So here's what we're doing, folks. Now that we've sort of drawn the thing anyway, here's our length, and the length of that would be 4 minus, because this is y is equal to 4 minus x squared. I can't write. Okay, if I could, let me see if I can clean that up just a tad. Okay. Okay, 4 minus x squared. So the height of that and the y is equal to 0, that's always going to be 0. So that's the height. And then the width of this is your dx, right? So that would be dx. I just did the accumulation thing. Whatever. Okay, let's do that. That would equal to, what's the antiderivative of 4 minus x squared? 4x minus over 3. Evaluated from 0 to 2. Okay, that'd be 2 times, what did the first one give us? 8 minus 8 over 3. And the second part will give us? Nothing. Yeah, 0. Nothing. Absolutely nothing. Okay? So, if we wanted to do that calculation, when I lean on this, it seems to do strange things, so I'll try not to lean on it. Okay, what does this become? 2 times, one way to do this is get 8 over 3, 8 as how many thirds? How many thirds is 8? 24 thirds minus 8 thirds would be 16 thirds, and twice that is 32 thirds. That's the area of that. If you wanted to get it into maybe a second?
10 and 2 thirds.
10 and 2 thirds, yeah. That's exactly what I was going to say. There you have it. And they did that. Now, for the life of me, I do not know why they go to this extent. But you got the right answer. Okay. Now, I'm going to clear what we've written. Is that okay? Everybody got it? Okay. Take your time. Okay. All right. To me, that was the accumulation. Is 0 to that. It's getting more and more and more. Okay. Whoops. I meant to erase first. I said I was going to, and I didn't. Okay. The area of that region is the area from -2 to 2. They didn't show how they got those limits, but we know how they did. 4 minus x squared dx. That's your height times your thickness, your width, being the dx. You can think of the integration as the accumulation of the area of the rectangles formed as a representative rectangle slides from -2 to 2 as shown in this figure. Yeah, this is what I think of every time you're back on it. You know, no, goodness gracious, this is far too tedious. That's when you're going from -2 to 2, you haven't even started. You're just right there. You haven't covered any area. Then if you go to -1, you've covered that much area. I'm going to go through the effort to do that. Yes, I definitely will. And then I go to 0 and I get that far. If I had done this, when I got to 0, I'd double that and be through, okay? But no, they're going to go to 1, you know, and increase that. And because they just love doing that interval over and over and over again. And then finally do that. No. I'm going to do sort of like that. I'm going to take this half and just do it once, double it, be through. But you see, that is letting this representative strip, which grows in height and then reduces in height, and you're adding that each time. That's what they call it an accumulation process. Why? I don't know. That doesn't add any great insight to me. It actually is tedious, okay, in doing more work, which I love doing, okay. All right, that was example 6. The integration part was the easy part, okay. So let's look at homework exercises for example 6. Do any of the odds 5 through 9. I've given the, do all the ones 5 through 9. The answers for 5, the odds 5 through 10. Do all of them 5 through 10. You should be able to do those. The answers for 5 through 9 are at calcchat.com, and for 7 is at calcview.com as well. Excuse me. Goodness gracious. For some reason, this room to me feels overly hot. Maybe I'm just moving around too much. It just clogs up my head like crazy.
It got really cold this morning.
What's that?
I was saying it got really cold this morning, but out of nowhere it just started heating up.
Yeah. And last night we turned on the heat for the first time. And of course, the first time we turned it on with the furnace and stuff, the coils, you know, got a little dust on them. They're burning off, and it was, but I'll live. Okay. Do either 11 or 13. They're both at Calc Chat. 11's at Calc View. Do any of the odds 15 through 27. They're all at Calc Chat. 17's at Calc View. Do number 29. It's at both Calc Chat and Calc View. Do any of the odds 31 to 35. They're all at Calc Chat. Any of the odds 37 to 41. They're all at Calc Chat. 37's at Calc View. Do either 43 or 45. They're both at Calc Chat. 47 or 49. They're both at Calc Chat. Do 51. It's a Calc Chat. Do either 53 or 55. They're both at Calc Chat. 53's at Calc View. Do either 57 or 59. They're both at Calc Chat. 61 or 63. They're both at Calc Chat. There's an exploring concepts. There's 2 of them there, 65 and 67. I'm assuming they're both at Calc Chat. If they're not, if you get hung up on this, don't worry about them too much. You can do 69. It's talking about dividing a region into 2 regions of equal area. You should be able to do that. We did that one just on that last one we did. 71 is another one you can do if you choose. 73, they're all at Calc Chat. 75 is a Calc Chat. And then there's a Lorenz curve that you certainly can do, but the other thing you can do from that is say, well, who in the world was Lorenz, okay? And I think you may find he's not actually a mathematician. He probably, it seems like he was an economist, but he used math. So if business or economics or something like that is of interest of yours, that may be a good paper topic, okay? 79 is a building design problem, so you can try that one if you'd like. It should be a Calc Chat. 81 is an area problem. It should be a Calc Chat. 83 and 85 are both true false. They should be at Calc Chat. And then the Putnam challenge, only if you want to take a look at it. All right, that was finding area. Oops, hit the wrong key. All right, so let's move on to 7.2. Okay, These are applications of integration. Area was one application. 7.2 introduces to another. If it'll come up, here it comes. PowerPoint has been slow today. Here we go. Not too bad. Oh, man. Wish I could breathe better. All right, look at the slide from the current slide. All right. Here we're going to be talking about calculating volume. And in 7.2, we're going to talk about one method they call the disk method. 7.3, we'll hit another volume method that will be called the cylinder method. But let's start with the disk method. Okay? So we'll find the volume of a solid of revolution using the disk method. We haven't told what it is, but that's what we're going to be doing for our objective. Find the volume of a solid of revolution using the washer method. Okay? Just like the dish method, only a little bit. And we'll find the volume of a solid with known cross sections. Okay? Sort of an application type thing. So let's go from there. Let's first talk about the disk method. All right. When a region of the plane is revolved about a line, the resulting solid is called the solid of revolution. The line that it's revolved around is called the axis of revolution, wherever that is. It doesn't have to be the x-axis or the y-axis. It can be any line, anywhere that the solid is revolved around. Okay. Now, if you think about it, please do, there is some curve there, okay, that's defining the solid. And we always do the incremental thickness of that, the area under that curve, as some width, usually a dx, it could be a dy, times a height, which could be that way if you had dy, okay, which is a length times a width. But if you're going around this line right here, then and this is going around here, this will also be the radius of that solid of revolution. So that's why they called it R rather than L. Normally we would say length times width. Now it's the radius times the width. Okay? Now, the simplest such solid is a right circular cylinder known as a disk. So if you just take this line and rotate it around the x-axis, okay, then you're going to get a solid disk that looks like this. Circular this way, that thickness that way, the width thickness that way. The radius of the circle that you get from revolving it around there is going to be what we're calling your R, or it could have been the length of that rectangle, or it could have been y if that's the, if this is the x-axis, then the r would have been how high y is. Anything like that. You revolve that around the x-axis, you get a disk. Okay? Now, this is a finite disk of some thickness w. What if this was an incremental element? Then that could be a dx. This is the x-axis, horizontal axis. And then your r would be some function of x, which would be your curve that you're talking about here. But what is the volume of that thing? The volume of a disk like this is the base, which is a circular base, pi r squared times the width. So pi r squared W. That would be the whole volume of that cylinder. This is a simple right circular cylinder. Now, like I was saying, if this is just a little portion of a shape, then that would be a pi r, which represents the function value, squared, and then rather than W, it would be a dx. Okay? And then you sum all those little disks into accumulate them, like we were talking before, into the whole solid structure. So the volume of such a disk is the area of the disk, pi r squared, times the thickness of the disk, w, width of the disk, where r is the radius of the disk and w is the width. And here's that. All right. We did have every other person here. Now we got one more than every other person. Okay. We're on page 454, right near the bottom of the page there, I think. And it's section 7.2 in chapter 7. All right. R is the radius of the disk, and which think of that as being your function value, your y, and then w is the width of that disk. Think about that as being your dx in the future. Delta x right now, and then later dx. Okay. All right. This is just past the middle part of page 454. Now, sorry. I seem to be losing my voice again. Don't know why. So, this time, what we're going to do is find the volume of a general solid revolution. It isn't just a simple disk. That was easy. We already knew that. Pi r squared h, or where h is the height. They just gave the disk. Okay, width. Okay. Now consider a solid revolution formed by revolving a plane region about the indicated axis. Okay? In other words, here's the shape under this curve. All this y is equal to f of x, right? And you're going to revolve that around the x-axis. Okay? And you're going from x equal a to x equal b, that portion. Sort of looks like a Christmas tree stand, right? So, okay, that's what that curve is going to do. Well, for any given rectangle representing the area of that curve, your r is your function value, f of x, like I was saying before, but this is your x-axis, this is y. That's the y value here, times your delta x. That's going to be the area, and the area you're going to rotate around there. So it's pi r squared times delta x. Okay? Now, what you get by revolving that, just this portion around there, you see this sticks up a little and dips a little there, and this is what you have there. To me, the drawing isn't all that useful, but it kind of is. I mean, I can see what they're doing. But that would be the disk. This disk represented going around that. The rest of it is the shape. Okay? Again, that's delta x. Okay? Now, again, the r is whatever the height was there. It's your f of x times your delta x. Okay? That comes up. 2 pi r. 2 pi times f of x times your delta x. Okay? So if you did this strictly in disk like this and had several of them, this is your approximation of the shape that we could get from that. Not a great approximation, but kind of adequate. And here's Daniel. Okay. So the first part of the alphabet is doing quite well. Clark is holding the last part of the alphabet by himself. Okay. Heavy load. Okay, he got it. Okay. So that's going to be how we're going to approximate this shape. Guess what we're going to do? We're going to approximate it with this, but what are we going to do with these delta x's?
Smaller and smaller.
Yeah, smaller and smaller and smaller until they approach 0, and then you got a continuum of them. You're adding them together, which is your integration rather than sigma. Adding these discrete ones together we're going to go to an integral, which is going to be an infinite number of them together. Okay, to determine the volume of the solid, consider a representative rectangle of the plane region, just like we did before. When the rectangle is revolved about the axis of revolution, it generates a representative disk whose volume is delta V, and that would be pi r squared, where the r is usually your f of x, times your delta x. And then if we let that delta x go closer to 0, this will be going closer to 0, but these will be the incremental pieces you add up using that. So approximating the volume of the solid by n such disk. So now we're doing something that's equivalent to those Riemann sums that we did. You know, when we're adding those little rectangles together, now we're adding these little disks together. N of those, width delta x and radius r of x of I, where I goes from 1 to n, because you have n of those disks right there. That produces a volume of the solid, or something approximating the volume of the solid. The summation of I is equal to 1 to n, you got n of those disks, of pi, that's just a number, that could come on the outside. Your r sub x of I, r of x of I squared, pi r squared, times your delta x. Pull the pi out, like I said, and then that would be the summation r of x of I delta times delta x. R of x of I squared. Okay. Oh man. It's just getting more and more clogged. Okay, that approximation appears to become better and better as your delta, as that partition of your x's is approaching 0. That's the largest partition of the x is approaching 0. The n is going to infinity, so you can define the volume of the solid as this limit of this thing that we had before, as that partition is going to 0. Pi, that pi was on the outside, this pi can come outside the limit even, you know, because it's just multiplied by it. The summation of I is equal to 1 to n, but now n is going toward infinity, it's just getting smaller and smaller. R of x of I squared dx. So pi r squared is your area of that times dx is the thickness of that which you have. And the limit of that happens as the delta goes to 0, the partition goes to 0, so n is going to infinity, that leads to the integral. The summation becomes an integral. A to b pi on the outside, the integral a to b, r sub x, r of x squared dx. Okay. So schematically, that's how you like to look at it. This method looks like this. The known precalculus formula, the volume of disk, pi r squared w. Okay? Now, an incremental portion of that for small w's, which we're going to call dx's, that would be delta v is equal to pi r sub x of I squared dx, what your smallest okay. The w is becoming a dx there, and this will be a little increment of that volume. Okay, and then you integrate this, and that gives you the volume of pi. And this goes from a summation to an integral from a to b of r sub I, or r of x squared dx. So you need to be able to get that radius function as a function. Integrable. Okay. So a similar formula can be derived when the axis of rotation is vertical. To find the volume of a solid of revolution with the disk method, use one of the formulas below. The horizontal axis, now this, catch this folks, This is always assuming the bottom of that graph is the x-axis. This was assuming it's the y-axis, okay? If it's anything other than those, we're going to get into what we're going to cover next, the washer method. But this will be the disk method. Or, there are a couple of other variations on the theme that we'll get to. So we'll get there in a minute. Okay, so it's the horizontal axis of revolution. You're going around that axis, and you're starting from that axis. The volume V is going to be pi integral from A to B, the radius thing squared, which is usually your function value, times dx. Okay. Why they're continuing to call it r of x, which is fine. You can call it anything you want to. Usually we call it alpha. Now, if the axis of revolution is around the y-axis, then it's a better idea to take the delta y's, because your delta x's, we'll do that in the next section, delta y is going to be the thickness of that disk that goes around. You're going to sum from C to D then, okay? So the volume would be pi integral from C to D, r of y, so now you have to get this is a function of y, not a function of x. Okay? So if you're given a function of x, if you want to do this method, you have to change, manipulate the function so it's a function of y squared dy. dy replaces delta y. Dx replaces delta x. Okay. So here's example 1, which is top of page, or near the top of page 456. Find the volume of a solid formed by revolving the region bounded by the graph of f of x is equal to the square root of sine x. Okay. Rather bizarre kind of little formula here. Okay? Now, you might ask yourself, what in the world does that look like? Well, it's fall in Alabama. It looks like a football, right? Okay. When you revolve that around there. Okay. Believe it or not, that is indeed what it looks like. Now, here's why it wasn't looking more like a circle. And it wouldn't have been exactly a circle, but it would look more like it if you had f of x is equal to sine x, not square root of sine x, okay? Because the sine x won't be a circle, but it won't go up as fast here. In fact, it's sort of linear in how it goes up here, and then reaches the same height and then comes down. So in between 0 and 1, the square root goes up more quickly, and then comes down more quickly over here, whereas square root of, just sine x would go up much more regularly there. Still would be an odd shape. It wouldn't quite be a sphere, but it would be a little bit closer to one that would be, perhaps. Not that that matters. Okay, so the volume of a solid formed by revolving that strange function and between that function the x-axis, but we're only going from 0 to pi. Why would that be? What happens to sine x past pi?
It's negative.
Goes negative. Think you can do that there? No way. And you can't do it this side of 0 either, because that would have gone negative. Can't take the square root of a negative number. But you can have that positive number between 0 and pi, so we even have the equal sign there, meaning 0 at each end point. Okay. So, oh my goodness. sort of has pointed ends here, but it's close enough for a fallen elephant. Okay. Anyone want to hazard a guess why they use the square root of sine rather than sine? We already said basically it's going to keep you between 0 and pi, but we could have done that anyway. What's the first thing you're going to do with that?
Take a derivative.
It's what?
Take a derivative.
Not yet. We're in integration now. Okay. So that answer isn't as good anymore. It used to be pretty good. But, if you remember the thing, you're going to square it. And if you square a square root, you wind up with sine, and that's going to be a piece of cake too. Whereas if you wind up with sine squared, not going to be as easy to do. In fact, not easy at all. So they were kind to us by giving us what looked like a more complicated f. It actually becomes simpler because what's the formula for that? Oh, I'm sorry. Hit the wrong key here. What's that formula? Formula for that, or you don't have to remember the formula, just look at the picture and do. Volume is equal to
Pi times radius squared.
Okay, say that again.
Pi times radius squared.
Okay, yeah. Pi goes on the outside, the radius on the inside, and I just let my pen drop and it made a mark on the paper. Goodness gracious. I may have to do a timeout and go get something to drink because my head is just clogging up like crazy. I hate to have to do this. Let me just do a pause here. Okay, sorry I stopped in the middle of it. And like I say, I'm not sure it's a lot better now, but let's try. Okay, so the volume, goodness. Let's go back up to here. Volume is equal to pi integral, what we were calling r of x squared dx, okay? Now where did that come from? Often they show the r here too. But see, the r now is your f, okay? But where that came from was pi r squared is the area of the disk of revolution there, where r is the radius of revolution, which now we're going to call our f, okay? And the dx then is the thickness. That's your accumulation model, I guess you would say. So in this case, the r of x is your f of x. So we'll write it that way here. So this would be the pi on the outside, because that's just a constant, f squared of x dx, or f of x in parentheses square, however you want to say it, dx. Oh, and this is going from 0 to pi here. This is a definite integral, 0 to pi, and then that pi, don't confuse the two. This is part of the problem, that's part of your formula, okay? And this will be pi times the integral from 0 to pi of the square root of sine of x dx, but that square root of sine of x is squared, which of course becomes, I'm writing all the steps in here now, after a while we'll skip some of these, pi times the integral from 0 to pi of, and what's the square root of sine squared? Sine. That would just be sine x dx. And I think we can do that, can't we? Pi times antiderivative for sine. Okay.
No, negative.
Negative cosine. Very good. Evaluated from 0 to pi.
How did you get negative cosine? Because I know that's
okay. We don't really need that last bracket. Okay. We're talking about the antiderivative of a sine. Well, what is the function that when you take the derivative of it, you get a sine? Cosine, except the derivative of cosine is minus sine. So therefore, the antiderivative of a positive sine would have to be the minus cosine. Okay, so that's where that comes from. Okay, now let's do the calculation. The pi out front is out front. Don't sweat that yet. Now, let's do minus the cosine of pi. What is the cosine of pi?
Zero?
No. Cosine of pi halves is 0. Okay. Cosine of 0 is 1. Cosine of pi is negative 1. So that would be minus a negative 1. Okay. Now we've got a minus, right? Because you're doing the second variable, that gives you a minus, but the cosine is minus. That's going to be a plus. And what's the cosine of 0? 1. Okay. So this will be 2 pi. Because negative, the opposite of negative 1 is 1, plus 1 is 2, times pi is 2 pi. So there's the volume of that football sort of shaped thing. It's going to be 2 pi. Amazing, kind of, but true. Okay? And that's exactly what they got here. Okay? Now the key here is, well, I guess several keys. Do your integration. We'll identify what is your radius. That really is the first key. Okay? And since you're going from the above the x-axis, it's just going to be the function value. Okay? And the function value was square root of x. So the area of that disk would be pi r squared. But the r is square root of sine, so it would just be pi times sine. Pull the pi on the outside, and we're going to integrate that sine from 0 to pi. That's where it intersects the axis, 0 to pi. And when you integrate that, you get a minus cosine, and then plug that in, and you get the minus 1 plus 1, and that gives you your the entire volume then. Okay. The area of the disk times the thickness of the disk, which is your dx. Okay. That was, though it looked like a weird one, it was fairly straightforward. All right to do a, to erase it?
Yes.
Okay. We'll see how they did it. The other thing is, this computer is always putting out heat, so I'm breathing the hot air coming out of that, and it probably has dust in it too. So, all right. From the representative rectangle in the upper graph, okay, you can see that the radius of that rectangle will be your alpha x. That's going to be the height. That's going to be the radius. Okay, so that took care of that part of it. Then, oh, and that alpha x is square root of sine x. They threw that in there too. So when you use the formula, so the volume of the surface of solid of revolution is going to be the pi that you can pull on the outside because it's just a constant. Integral from a to b. We have they already told us what it is, but they're putting a to b in there again. R of x squared dx. That's the basic formula for the disk method. Okay? Pi r squared is the area of the disk times the thickness of the disk. That's going to be the volume of the disk. Okay? And then sum all those up with the integration. That's how you think about it. Okay? Now, plugging in what we know, that's pi, the a 0, the b's pi, so that's two different pi's there. Sine, the square root of sine x is your radius function, your alpha of x. Square root of that squared, then, that removes the square root symbol. and you just have the pi times the integral from 0 to pi of sine x dx. But when you find the antiderivative of sine x, it's minus cosine x, so pi times the minus cosine x evaluated from pi 0 to pi. And how you do that, just a reminder, pi times cosine, minus cosine of the top, minus a minus cosine of the bottom. Okay, that's what you got to do. It's the top minus the bottom, but the thing is a negative to begin with, so that would be a minus 1, which is 1, minus a minus, which is plus 1, okay? And that gives you your 2 pi. Those negative signs will reach out there and trip you more often than just by anything else. The calculus part of it is so easy, it's just the evaluation part with all those minus signs. The minus sign from the function, the minus sign from your fundamental theorem of calculus, alpha b minus alpha a, that minus sign, and then what cosine was a minus, so you just have a whole string of them right on top of each other. All right, that was example 1. Before we go to washer method, there is an example 2. You want to do that in class?
Yes.
Let's do. I don't think we can go one more. Okay. Example 2. Find the volume of the solid form by revolving the region bounded by the graphs of f of x is equal to 2 minus x squared and g of x, which is 1. About the line x equal 1. No, y is equal to 1. I was going to say that I don't think that will work too well. Okay. Okay. Y equal 1. As shown in the figure here. Well, if you don't have your book, you don't have the figure. All of you have book. No one doesn't. Okay. Oh, you have a different book. Yeah, different book. Okay, so let me show this one. All right. Find the volume of the solid form by revolving this region by the graph region bounded by the graphs of this and g of x equal 1 about the line y is equal to 1. Okay. So let's draw our graph here. All right. Okay. Not very even spacings here, but live with it. All right, how do we graph 2 minus x squared?
Go up 2.
Go up 2. So when x equals 0, you're at plus 2. Okay. At x equal 1, that would be, y would be 1, right? Plus or minus 1 would be at 1. Okay. If x equal 2, you're off scale, but we can do that. That would be a minus 3, no, minus 2, right? X equal there. So did I do that? Oh, yeah. Why is it? Okay. Looks like it's something, and it, mostly because of my lousy spacing, it's something like that. But it's not this region here, because it doesn't say between that and the x-axis. It's between that and the g of x equal 1. F of x is that, g of x equal 1. Well, g of x equal 1 would be, oh, I guess I should make it a solid line. I can't draw straight lines, but you get the general idea. So it's g of x is 1. This is f of x equal 2 minus x squared. That's that parabola. And this is g of x equal 1. So that really cuts us off up there. But what are we revolving that around? We're revolving it around the line y is equal to 1, which is g of x equal 1. So it's going to go around there. So that's even more of a little football like this. When you revolve that around, then you have this kind of notion. And there's your dx. Okay. All right. Now, that really does look more like a football this time, right? It's ball. Okay. Gotta look like that. Okay. So your dx is the thickness of it. Now the question is, what is your radius? Not quite. What we're revolving around this line, y is equal to 1, is that little circle there. Okay? So that is, the radius is right here. Can I put it in a different color because it's so crowded it may be hard to see? What color you want?
Red.
Red. Okay? Red for radius. Okay? The radius here is that. That's your capital R of x. Okay? And what would that be? We mean that length. Well, the upper end of that length is uh, 2 minus x squared. We have points for that to be plotted. 2 minus x squared. Okay. Minus, that's the upper one, minus the lower one, because the length is the difference between those, minus 1. Okay? So that would be 1 minus x squared. That's your radius. Okay? That is the radius. And you're going around there. Your dx is what we've already said. So your, can I go back to dark color again? Okay. So your area of that region is going to be pi times the integral. Oh, what are those endpoints? Well, we're sort of lucky. We had already figured them, hadn't we? Minus 1, 1 and positive 1, 1. So basically, it's going dx from 0 to 1. Okay? Not quite. Why did I do 0 to 1? I'm going to double it. So I need a 2 out there in front of the pi because that's symmetric. Okay. So 2 pi times the integral of 0 to 1. But what's my radius now is this thing. So it's a 1 minus x squared. Squared. Remember, you have to square that radius. Pi r squared. I mean, I always thought pi were round, but never mind. Okay, and then your thickness is still the dx. Okay. Now, how would you approach integrating that integral?
Taking first squared.
Okay, now you could do it maybe with a chain rule type concept. I think far easier going and square it. Okay, it'll be 2 pi times the integral from 0 to 1 of, what do you get when you square that?
1 minus x.
Minus what?
Minus x.
You're not taking the square root wrong. You're that would be taking the square root wrong, but you're squaring it, and let's do it right.
The x to the 4th.
Okay, but you got more.
dx.
2x squared plus x to the 4th. Remember that? If you don't remember it, go off to the side and square it. 1 minus x squared times 1 minus x squared. That's what it means to square it, right? And for all that, you get a 1. Then you get minus x squared minus another x squared. That's minus 2x squared plus x to the 4th. Okay? That's your integral, your integrand. And you're happy about it. That's why you got a smiley face there, right?
Yeah.
Okay, yeah. Okay, good. Okay, and then the dx is the thickness. Let's carry it over here so we can see it better. 2 pi. And what is the antiderivative of 1? Huh?
0.
No.
X.
X, yeah, you're not taking derivative, antiderivative. That'd be x minus
2x cubed over 3.
Okay, a little louder.
2x cubed over 3.
Yeah. Minus 2x cubed over 3. And the last part,
Plus x to the 5th over 5.
5. Okay. And that's evaluated from 0 to 1. Okay, you got the 2 on the outside. That's why you're able to do this. Okay. I think I'm going to write above because I'm running out of room below. Can I go and erase the graph? Because it is getting crowded. Do we need it in it for anything else? Okay. So I didn't need to draw my line through there, but I did. Okay. Trying not to erase anything I might need. I don't think I need that anymore, so I sure hope I don't need any of this. Okay. And I think that was just scratch work too, so let's get rid of it. Okay. I think that's going to give me enough room to write. That's going to be 2 pi. Now let's plug and chug here. What do we get? Plug in the 1. 1.
Minus 2/3.
2/3.
Plus 1/5.
Plus 1/5. Okay. And then when you do the minus part with the 0, I can do that 0. It's all zeros. So this should be our answer. I can't read my writing, but I'm pretty sure that's the 2/3.
Yes.
Okay. 2 pi times, what's your least common denominator?
15.
And how many 15s is 1?
15.
15 minus how many 15s is 3? Is a third.
10.
Okay, yeah. 5 times 2 is 10. And how many 15s is the last one here? Huh?
3.
3, okay. 3 15ths. Wait. All of that over 15, sorry. Okay, that's why I did it, was just combining all those. So 5 minus 10 is 15. I can't talk. 15 minus 10 is 5, plus 3 is 8/15. So this will be 2 pi times 8/15, which is going to be 16 pi over 15. Okay. That, they say, oh, look at that. The book got it too. 16 pi 15. Which is something maybe getting close to 4 cubic units, whatever they are. It's 3 and a fraction for sure. I'm so sorry that I have all this congestion. Okay, does that make sense? Got it? All right, can I erase? Okay. All right. Now we move I don't know why it made a noise at me. Okay. We move to the washer method. What is a washer as compared to a disc?
What is a washer compared to this? Although they send it with that flat on the side.
Well, you got a hole in it, right? A washer has a hole in the middle of it, right? So it's just like a disc, only it's got a hole in the middle of it. Now, where does that come from? This method can be extended to cover solids of revolution with holes by replacing the representative disc with a representative washer. Okay? Now, you can do it with 2 washers. You could do, with 2 discs. Do the outer disc and then cut out the hole and subtract off the inner disc, which basically is what we're going to wind up doing, okay? But they like to act like they're subtracting off the radius to begin with, but really we're subtracting off the disc that's in the middle, okay? The washer is formed by revolving a rectangle about the axis, just like we did before, except now we have a hole, and that hole is the little r here. So we're doing this part around the axis, leaving us a hole of diameter 2r, radius little r, in the middle, like you see here. If little r and big R are the inner and outer radii of the washer respectively, then W, and W is the width of the washer, then the volume is, the volume of the washer, why do they say the volume is and the volume of the washer equal? Seems like we only need to say that once. Pi times the difference of, see what you're doing is pi capital R squared W, which is the outer disk, minus pi little r squared W, which is the inner disk, subtracting that away, so it just becomes, if you factor out the pi here and the W there, you just have the, with W being the width of it, okay, later it's going to be dx. That's what you would have. Okay? Now, to me, it's just easier to just look at it and think through it rather than trying to memorize the formula. If you like formulas, there's the formula. Okay. So to see how this concept can be used to find the volume of a solid of revolution, consider the region bounded by, the outer radius, capital R of x, and the inner radius, little r of x, is shown in this figure. So here's what we've got. We've got a plane region here. This happens to be an f of x, looks like a linear function here, minus a, looks like it could be a parabolic function there. That's your little r of x. And then that's going to be your height. What is the height? The tall minus the short. Okay? But that's not what we're doing here. Shouldn't have even said that, perhaps. You're doing the outer minus the inner. So you square that first before you do the area. Don't do the area of the rectangle. Okay? Yeah, well, you kind of do too. You do the area of the little rectangle you don't see, and then subtract the area of the rectangle. Do the area of the rectangle from the top of this one to the bottom here, which doesn't include this rectangle, but do the entire larger rectangle, this area minus the area of this, volume of this one minus the volume of that one, and that gives you what you got. Now, what this is a, is that a strange looking Christmas tree stand? You have a hole in the top, a bigger hole at the bottom, but you have curved sides there. Inside, not the outside. The outside is a slant. The inside is curved, so I don't know why you would do that as a Christmas tree stand, but you could.
Almost like a lamp or odd-shaped lampshade.
It could be an odd-shaped lampshade where you have an interior that's curved in, but the outside is not. Yeah. So yeah, it could be that too. Okay. So, with that figure in mind, if the region is revolved about the axis of revolution, then the volume of the resulting solid is V is equal to pi. That pi is going to come from both of those volumes or areas that you're going around. A to B, whatever your limits there, or on your X, and then the capital R squared of X, which gives you the volume of the outside disk minus the volume of the inside disk, which cuts the hole in it. That's what gives it the hole, and that's what you're doing. Don't do big R minus little r and then square that. That's not going to give you the right answer. Okay, this is what will. Note that the integral involving the inner radius represents the volume of the hole and is subtracted from the integral involving the outer radius, which would have been the whole disk, the big disk. Okay, so you're subtracting the little disk, which is the hole, from the big disk, which is the whole solid. Okay, so that's why you square them before you subtract. Okay, so here's example 3, and that is the next one that shows up here. Find the volume of the solid formed by revolving the region bounded by the grass top. Y is equal to square root of x. Now that starts at 0, 0, goes to 1, 1, and then to 4, 2, and then it keeps on going there. But we're not going that far. And y is equal to x squared, which actually starts smaller and then increases. It goes to 1, 1. That's the parabola on the bottom and the square root, the sideways sleeping parabola on top. Okay? Now, it's okay to do this, but to me, this almost always makes me want to do the area of that rectangle. We don't do the area of the rectangle. You do the outer rectangle minus the inner rectangle. Okay? So you don't start trying to do the difference of those. Okay? So, your capital R is the square root of x, and your little r is the x squared. Seems sort of backwards. It seems like you should be doing it on the other order, but you don't. This one's on top of that. Anything past that, you would have been. Because then the x squared takes off and the square root of x is left. So if you're doing something out here, then the x squared is first and the square root of x is second. Not what we've got here. Okay, from 0 to 1. So there's your solid of revolution, and I can't think of what to call that. Curved, strange curved inner surface, but a regularly curved. In fact, that's a spherical curve is what you see on the outside, and then whatever that strange curve is on the inside. Revolving that around the x-axis. Okay? Anyone? Let's see if they give us room. Yeah. You can see the outer radius, inner radius are as follows. Outer radius is that. You tell me what the inner radius is.
X squared.
X squared. Okay? All right. Let's pick up and go from there then. What's your integral? sorry, I started to say area, I mean to say volume. What is your volume equal to? Pi on the outside.
Integral of 0, well, I mean from 0 to 1.
0 to 1, perfect.
And we have square root of x squared minus x squared
dx. Got it. Okay. Your pi times the outer is going to be the outer disk minus the inner disk times the thickness of the disk. That gives you the washing. Okay. So you tell me what your integrand is now. Integral from 0 to 1. We still got that. What is square root of x squared? X minus x to the fourth. And that's what we multiplied out the dx. So now let's do the antiderivative of x. What does that give you? X squared over 2 minus
x to the fifth over 5.
Minus what? Oh, over 5, I'm sorry. And that's evaluated from 0 to 1, which is not too hard to evaluate. It'd be pi times 1/2
minus
1/5. I'll do the 0 part. Okay, done. Okay. And what's the least common denominator here? Okay, how many tenths is 1/2? 5 tenths minus 2 tenths. So that would be 3 pi over 10. Let's see, that's a pretty small volume it seems like. Yep, 3 pi tenths. Perfect. Okay. That's something close to 1. Yeah, because pi is 3.14. And 3 times that would be 9.4 something another over 10. Yeah. Getting pretty close to 10. I mean, to 1. Goodness gracious. All right. Let's see. Oh, that's how we did it. Let's see how they do it. I bet you it's somewhat similar, don't you think? Okay, your capital R is, oh yeah, it was already up there. I put the little r as x squared. And then the volume, just from your thing, is pi times. Pi times the capital R squared would be the outer disk minus the inner disk, which is going to be your whole pi times the little r squared, all multiplied by dx. It gives you the integral from 0 to 1 times the integral of square root of x squared, sorry, my eyes are messing up, minus x squared squared, just like we did. And that would be pi times the integral from 0 to 1 of x minus x to the fourth dx, which the calculus is the easy part. It's pi times x squared over 2 minus x fifth over 5, evaluated from 0 to 1. And that gave us 10 well, they just magically go from that to that, you know. But we did the work and we know what it is, the least common denominator of 10. So that would be 5 tenths x squared well, easier to go and evaluate. It would be 1/2 minus 1/5, least common denominator 10, so it would be 5/10 minus 2/10 is 3/10. And then 3 pi over 10. 3/10 pi, however you want to call it. Same thing we got. All right. That was, okay. That was example 3. I was making sure they weren't skipping an example here. Oh, man. Okay. Each example so far, the axis of revolution has been horizontal, and we've integrated with respect to x. Example 4, on the other hand, is going to have the axis of revolution vertical, and in that case, not all cases, we'll find out this next time, we'll integrate with respect to y. So in this example, example 4, you need 2 separate integrals to compute the volume. In reality, we've always had the 2. We just combine them into one. This time, we'll actually separate them. Now, this isn't because it's with respect to y. It's because of the shape of this thing, okay? Find the volume of the solid formed by revolving the region bounded by the curves. Y is equal to x squared plus 1, which is this parabola up here. It's the basic parabola, vertical shift up to here. So there's the first parabola. Y is equal to 0, which of course is the x-axis. X equals 0 is the y-axis. And x equals 1 about the y-axis. Oh, x equals 1. I was going to say, you don't need that. Yeah, I wonder why the blue line is there. And it's there for a different reason. X equals 1. And you're going to revolve that around the y-axis. Okay? Now, the reason you need 2 integrals here is the top half of this is going to be a washer, and the bottom half is going to be a solid disk. So that's why they split. It's not because you did dy's here. It's because your figure is that way. Okay? Now, here's the other thing about dealing with the y's now. They gave you y as a function of x up here. If you're dealing with a dy, then you need to get that as a function of y, not a function of x. Because you can't integrate a function with respect to x with making dy's. That just, it doesn't work, okay? So, what do we need to do to get that top function as a function of y? There's a fairly simple single phrase answer. Okay, you were going to solve for x, yeah. So the first step would be subtract 1 from both sides, and that gives us y minus 1 is equal to x squared. And then what?
Square root.
Square root. So x is equal to the square root of y minus 1. But actually, when I take the square root, both sides of an equation, I really should do a plus or minus. But looking at this, this is an x value, remember? We're over here, where x is always 1. So don't do the minus. We just ignore the minus. That would have been this half over here, which we're not dealing with. We're only dealing with the positive half, so only do the positive square root. Okay? So that's where they get the little r over here to be y minus 1. What's your capital R over here? Something like that.
Oh, 1.
1. Okay. The capital R is 1. Yeah, what is going on today? Okay. So your capital R is 1, and your little r for the top half is the square root of y minus 1. Okay. Always do big minus small. Don't do the other way. But not the function, the squareds of the functions. Okay? So, they take up so much room with the figures that you have very little room to write here. So I'm going to take that off because we already did all that. Okay. So the top integral is going to be what? Remember, you're doing a dy. I always like to do that first. For the top integral, what is the y going from and to?
0 to 1.
1 to?
Oh, 1
to 2. See the y's. You're doing dy's here.
Okay.
So you're doing 1 to 2. You got your pi out here. You always have the pi out there. Okay? Don't leave the pi out in the rain. Never mind. Okay? And what would be your integral?
1.
1 squared, actually, which is 1. Okay? That was being nasty. Minus
The square root of y minus 1 squared.
perfect. Okay? Second. And dy, you already had that written down. So pi times the integral from 1 to 2 of, I'll write down the 1, minus, and what do you get when you square the square root of y squared minus 1? Y minus 1. Okay? Then your dy. But notice here, your 1's, plus 1 minus 1, add the 0. That's a pretty simple integral. The integral of minus y evaluated from See, I did do that right, didn't I? No. When you square this, that's in parentheses. So they don't disappear, do they? They actually add in this case. Sorry about that. Like I said, those signs will jump in there and bite you where you don't want to be bitten. What does that give you? Pi times the integral from 1 to 2 of it's okay. This is 1 minus a y minus a minus 1, which would be 1 plus 1. It would be 2 minus y. Sorry, the reason I'm skipping some steps here is I'm running out of room, you know, and they have precious little room to write here, and that's the dy over here. Okay. Now can we do that integral? Anybody? 2y
minus y squared
okay, evaluated from?
from
1 to 2. I can't write, but it's something like that. Okay, so that'll be a pi, and then when you put a 2 in there, what do you get?
4 minus 1.
4 minus what?
1.
Try again.
Oh, 4 minus 2.
4 minus 2. That's the first part.
Minus 2.
2.
Minus 1/2.
Okay. It's minus a minus 1/2, right? Or did you put that in parentheses or something? Okay, you should have if you just said minus, because you see, again, the signs reach out there and nip you. Okay. What you have first, keep this sign the same when you plug in the 2. That would be 4 minus 2. Perfectly fine. Then minus a 1 in there, so that would be minus a 2, but then a minus, which is a plus 1/2. You see that? Okay. So that's a plus 1/2 there. Okay. And that would be, oh goodness, what does that become?
Pi over 2.
Second?
Pi over 2.
Pi over 2, you're absolutely right. So that's the volume of the top part of that, and then we add to that the volume of the bottom part, which is just simply your disk method, and that would be the integral, pi times the integral, from this goes from 0 to 1, since you're doing your dy's here, and your length here is just 1 minus 0. So what's that?
1.
Okay, so that would be pi times 1. Oops. Goodness gracious. Pi times 1. I went to erase and everything disappeared. Okay. So you have pi plus pi halves will be 3/2 pi. Now, for the life of me, I would have sworn that was more than half the one, that the bottom half, bottom part of that was more than twice the top part, but this says no, it's exactly that. So we got 3/2 pi. And look at that, the book got it too. Good for them. How are we doing on time? We're getting close. So let's erase what I've done, because it's all over the place here, because I just did so little room to write. Let's see what they do. For the region of the sphere, the outer radius is simply r is equal to 1. Okay? There is, however, no convenient formula that represents the inner radius, so you have to split it into two pieces. When y is between 0 and 1, then your inner radius is 0. But when it's between 1 and 2, the little r is determined by the equation y squared plus 1. Y is equal to x squared plus 1, which implies that y is equal to square root of x minus, okay, y is equal to square root of y. I keep saying it wrong. Little r is square root of y minus 1, just what we did. You subtract 1 from both sides and take the positive square root, just the positive square root. R is equal to square root of y minus 1. Okay. I sure would have wanted to write it that way. I don't know why they did. Okay, so your volume is then, they did the second one first. And why they put a minus 0 in there makes no sense at all, but it's fine. So it's pi times the integral from 0 to 1 squared dy, which comes up being 1 pi squared pi. And this one from 1 to 2, pi going from 1 up, y going from 1 to 2, of 1 squared minus this thing squared. Okay? Now, watching your minus signs there, this would just give you the integral of 1 dy, which I've already evaluated to be 1, okay, pi. And this will be pi times integral from 1 to 2. You get a 1 from here, minus a y from here, but plus a 1 from there, so that gives you 2 minus y. And that's your integrating from 0 to 2, from 1 to 2. And that would be, oh boy, they're dragging this out. That would be pi, okay? And this would be pi times 4 minus 4 over 2, which is 2. 4 minus 2 is 2. Minus a 2, okay? Minus a minus 1/2, so plus 1/2. And when you do all that, Oh, they did it all. Okay, I'm sorry. I thought they were going to skip all that. So it'd be pi plus pi times 4 minus 2 plus 1/2. This minus this minus this equals that. Okay. Plug in the upper and lower limits. And of course, the minus 2 is minus 4 plus 4 is 0. You're left with just 1/2 pi, which is then 3/2 pi. Okay. Good deal. Note that the first integral represents the volume of a right circular cylinder of radius 1, height 1. You could have just done that if you wanted to. Okay. The portion of the volume could have been determined without using calculus. That's what I said. Right circular cylinder, base times the height. Okay, area of the base times the height. Okay. Now let's see. That was example 4.
Just go to example 5.
Yeah, and I don't think we have time for 5 today, do we? No. Okay. So we'll be beginning example 5 next time. Okay. Let me give you a few homework exercises. In 7.2, you can do either 5 or 7. They're both at Calc Chat. 5's at Calc View. There's a little net running around up here, flying around up here. Do either 9 or 11. They're both at Calc Chat. 9's at Calc View. Either 13 or 15. They're both at Calc Chat. 13's at Calc View. 17 or 19. They're both at Calc Chat. 17's at Calc View. 21 or 23. They're both at Calc Chat. 23's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. 33 or 35, they're both at Calc Chat. 37 or 39, they're both at Calc Chat. 37's at Calc View. And any of the odds 41 to 47, they're all at Calc Chat. What do we still have to do? We can hold off and pick up the rest of those next time. All right, good deal.
See you on Wednesday.
Okay, have a good day or two. Take care.